Hello again. So welcome back. So we will continue with the keynote talk given by Nazım Kemal. He's from the Artificial Intelligence Research Center from the Istanbul Technical University and Eatron Technologies. So welcome, and I think we can start. Stage is yours.
Okay, thanks for the introduction, image. Let me get it full screen. All right, so you can see the screen clearly, right? I mean,
yes, it's good.
Okay. All right, let's start. Thanks for the introduction again, and also thanks for inviting me to this workshop. Hello, everyone. My name is Kemal, and I'm a professor at Istanbul Technical University and also the director of artificial intelligence at Eatron Technologies. And today I will be talking about sample efficiency in designing reinforcement learning algorithms for autonomous driving. So this is just a short, introduction about me. I will make this real quick. So my main research area is deep reinforcement learning and optimization, and especially application of these topics to autonomous vehicles such as self-driving cars and unmanned aerial vehicles. I'm part of a larger research group in Istanbul Technical University called ITU Artificial Intelligence and Data Science Research Center, where we collaborate with many professors to develop state-of-the-art AI algorithms. And I'm also the director of artificial intelligence at Eatron Technologies, which is a company that is focusing on developing software for electric and self-driving vehicles. And we conduct a lot of autonomous driving tests in both here in Turkey and also in the UK. Okay. So let's get started with some, very simple basic definitions. So most of the things that I'm going to talk about today is going to be application of reinforcement learning for autonomous driving. And if we want to recap, what is reinforcement learning? My favorite definition of this topic is basically it is machine learning for control. So unlike classical control approaches or classical optimization approaches, you do not have a model of the system, and your controller basically randomly interacts with the environment, collects data, and processes that data to develop a control strategy, which is usually called a policy. So it is basically about learning how to control a system by purely interacting with it and collecting and processing data. So reinforcement learning, or RL for short, has a lot of different applications. Virtually, you can apply it to any decision-making problem. But of course, today we are interested in applications to autonomous driving. And we have been working on applying RL to autonomous driving intensively for the last couple of years. And based on our experience, there are several clear advantages of using reinforcement learning for autonomous driving scenarios compared to other approaches. So I would say one of the main advantages is because reinforcement learning makes no assumption about the structure of the controller. It does not make any assumption about the model of the environment. It usually comes up with a better policy compared to classical approaches, such as the ones that you would use, such as the one that you would get using classical control or optimization approaches. Of course, there's a trade-off. It is much more difficult to train and develop RL algorithms compared to classical approaches, but when it is done right, usually you get something that is better than classical approaches. The second advantage is, which is actually my personal favorite, is everything you use in reinforcement learning is a black box, and in particular, your objective is a black box. So anything you care about, performance, safety, sensor uncertainties, traffic dynamics, etc., you can put that as those into your objective functions. So anything can be your reward or cost, which is again a very nice property compared to classical approaches, because in classical approaches your cost function needs to be differentiable, it needs to be integrable, etc. There are a lot of constraints. Basically anything you can measure as a performance metric, you can make that a reinforcement learning objective, which makes it especially appealing for autonomous driving, because usually it is not that clear what should be our objective when we are driving. And another nice property of reinforcement learning algorithms is they are problem-free, and they're adapted to the environment. You train one reinforcement learning agent for one particular condition, and then you can put it inside another environment, and it will start collecting data and quickly start adapting itself to the unseen and new tasks. So mainly because of all these appealing features, we really like applying reinforcement learning to real-life decision-making problems, especially for autonomous driving. But of course, having said that, these advantages also come up with a big disadvantage, and that is the sample complexity. Because reinforcement learning agents are making no assumptions about the environment, controller structure, and dynamics, it takes them usually millions and millions of samples to learn reasonable policies or effective policies. And because of this, we cannot really train reinforcement learning agents in real life, because we cannot afford to simply collect millions, billions of samples in real life and train an agent on it. And one of the reasons why we really love simulators and use that for applications like this is we can do what we call sim to real transfer. Like we can get a good simulator, we can develop a good simulator, train our decision-making agents, reinforcement learning agents in the simulator, and then hope that it is going to perform well in real life. So now this is kind of like the industry standard. If you don't have a simulator, you usually cannot afford to do reinforcement learning. So it might seem like having a simulator gets you out of the sample inefficiency problem, right? Because we always think that simulator data is free, simulator data is cheap. That is true up to some extent, but at the same time, even when you are taking millions of samples to train in simulators, there's also a lot of disadvantages that comes with that. The first reason is, if it takes like hours and months to train a reinforcement learning agent in simulator, your design cycles are going to be very slow. Because as with all machine learning algorithms, nothing is one shot. You are going to train an algorithm, you are going to see the performance in real life, and then you need to go back and retrain it based on your observations, right? So if your RL algorithm is sample inefficient, even training with simulators is going to take a lot of time. So simulations are not really, get out of jail card for sample inefficiency. Even when we are training with simulators, we need to be aware of sample complexity, and we need to develop algorithms and approaches where we can ensure that we are using these simulators effectively, so our design cycles are shorter, so we can train and deploy agents using shorter design cycles. And the main objective of today's talk is I'm going to present you 3 use cases that we have experienced over the last couple of years, where we were facing with this sample complexity problem when we were doing simulation-based reinforcement learning training. And we are going to look at various different techniques that really helped us a lot when we are dealing with this data and efficiency problems. And almost all of these are, by the way, research in progress. So most of these are preliminary results, but even with the preliminary results, we can clearly see that the future of simulation-based training and simulation-based verification is going to have some flavors of all of these approaches. Okay, so what are these 3 use cases? So the first one is going to be about using curriculums for reinforcement learning. Maybe some of you are already familiar with curriculum-based training from supervised learning. The main idea here is, instead of trying to learn a difficult task from scratch, we first give the agent easier tasks, and then we incrementally increase the difficulty of the tasks to smooth the transition. So by using less amount of samples compared to from scratch training, we can get better performance. So we are going to look at how we can use curriculums to address the sample inefficiency problem in reinforcement learning. And in the second part, we are going to talk about offline reinforcement learning. The main idea behind offline reinforcement learning is, what if we use RL on static data sets instead of, collecting data from our own simulators or our own interactions? Can we leverage existing static data sets on autonomous driving to get better driving performance? So that's going to be the second part. And finally, I'm going to talk about something that is currently in progress, which is what we call real-to-sim reinforcement learning. So, and this is going to be about how we can take what we have learned in real life and inject that back into our simulator so that our simulator looks more like real life, and iteratively we get better policies and better generalizability for reinforcement learning. All right, so let's start with the first one. So the first one is going to be about curriculum reinforcement learning. Okay. So direct reinforcement learning is difficult. And by direct reinforcement learning, what I mean is you take the task you want to solve, model it as a reinforcement learning problem, and then give it a reinforcement learning agent, then sit down and start the training and see if it converges or not. So like I mentioned in the beginning, this kind of direct approach usually is very, very sample inefficient. For example, on the left, you see a figure, a famous figure from the Rainbow DQN paper. So DQN is one of the most well understood and studied reinforcement learning algorithms in the past decade. And the performance curves that you see in here on the x-axis, you see millions of frames. Here we are playing Atari games, which is a very popular benchmark for measuring the performance of reinforcement learning algorithms. And on the y-axis, you see a measure of performance. So as the algorithms see more data, see more frames, they get better performance. But if you look at the unit of measure on the x-axis, you see millions of frames. So even to play simple computer games, these reinforcement learning agents might need to see millions of different examples. So even with the state-of-the-art algorithms, applying reinforcement learning directly to your target problem, it takes a lot of time to converge. And by the way, this is kind of expected, right? Because like I mentioned in the beginning, these algorithms learn by making zero assumptions. They do not know what an Atari game is. They do not know what an observation is. They do not know what an action is. They just receive raw observations, and then they try to find the correlations between your objective and your actions. And this is kind of like different than how humans learn, right? Whenever a human wants to learn a complex task, they never go on and tackle the most difficult task directly. Instead, we have curriculums, right? We start from easy tasks. We start from easy examples. And once we master the easy examples, we move on to the harder examples. So a reflection of this philosophy into the machine learning paradigm is called curriculum learning. And this is a well-studied subject in supervised learning. For example, if you want to apply this to an image classification tasks, you would divide your data set into subsets where you start with easy identification or easy classification tasks, and then you ramp up the difficulty as your algorithms gets better. And how do you transfer the knowledge between easy and difficult tasks? You simply apply a variety of different transfer learning algorithms, which are, again, very well known and studied in both supervised and unsupervised learning. Okay, so but how do we do that in reinforcement learning? How do we tell easy and difficult tasks from each other? So this is a very active research topic. A lot of people are working on it, but one way to do it is by just using heuristics. For instance, if you want to develop an algorithm that plays chess, you can do it as the example that you see on the slide. For example, we can start with a game where there are only pawns on the board. And then once this is mastered, so the algorithm will learn how to move the pawns and how to capture enemies' pawns. And then we can put a king in it. And then by incrementing the difficulty, we can get to the full chess game. And there are lots of examples and applications of successful demonstrations of showing that this can work in reinforcement learning. But application of this to autonomous driving is relatively understudied. There are some recent papers in this year's actually Intelligent Vehicles Symposium, but compared to all the other stuff that people have been doing, this is relatively understudied. So what we did was, can we take the same philosophy and apply that to autonomous driving scenarios where we can start from simple driving scenarios and go to more complex driving scenarios? And what would we see? Would we see any benefits? So that was the first question that we asked. And the second question is, how much does the curriculum matter? So if we come up with different curriculums, can we really identify what makes a good curriculum for reinforcement learning compared to another one? Okay, so of course, to do all of that, we need a good simulator. We need a simulator that can, capture all these different variations, capture all these scenarios. And for that reason, we are using a simulator called Simstar, which is developed by Eatron Technologies. It is based on Unreal Engine, and I'm going to show this real quick. So this simulator that we are using, basically, it can capture a lot of different road geometries. It is very easy to edit roads in it. And then we can easily put different dynamics. We can put computer vision algorithms on it. We can simulate different road conditions. We can simulate different weather conditions, etc. And this is something that we really need to develop all our reinforcement learning algorithms, because like I said, we want to see different effect of different weather conditions, etc. So for all the simulations that you are going to see today, they are going to be conducted on this Simstar environment. Okay, so what kind of curriculum are we going to come up with? Well, there are lots of different things you can consider between easy and difficult training scenarios, but by looking at, for example, analysis of road accidents, we can see that there are mainly three factors that makes it a difficult driving scenario versus an easy driving scenario. The first one is road geometry. It is actually evident that, especially for reinforcement learning, if you have a straight track versus a more curvy track, it makes it more difficult to master how to drive. If you have a straight road, like you see in the picture, then the reinforcement learning agent just needs to learn when to put a brake and when to accelerate. They do not need to learn any lateral control at all. But when there's a curved track, like the one that you see in here, or like the one that you see in here, then it also needs to learn how to control lateral deviations and longitudinal deviations at the same time. Another big difference is weather conditions. So to model that, we have got a clear weather scenario, we've got a rainy scenario, and we've got a snowy weather scenario. And how we differentiate between those, of course, apart from the graphics, we change the friction coefficient of the road. So for dry roads, we got higher coefficient, friction coefficient, and for snowy roads, we got lighter friction coefficient. And again, if you increase the adversity of the weather, it makes the more difficult driving scenario, because it becomes much more difficult to brake and decrease the velocity of the car. Also, whenever you are turning, you need to coordinate that much more precisely in order to not to get out of the road. And of course, there's the traffic dynamics. If there are other vehicles on the road, their dynamics, like how much unpredictable they are, that is also going to have a huge effect. So for today's presentation, we are only going to show the results on variation of road geometry and weather conditions. And we are going to ignore the traffic dynamics for now. We are working on it, but that is like a work in progress. And the idea is going to be, we are going to develop different curriculums where we start from simple road geometries and simple weather conditions and keep increasing the complexity of these scenarios. And we are going to develop different curriculums. And then we are going to test the effectiveness of different curriculums, like which one enhanced the performance, which one did not. And when it enhanced the performance, like what did we get? Like how much effective is this compared to training from scratch? And this is kind of like a template for our different curriculums. So here on the left-hand side, you see an example scenario. For example, we will start with a straight road in clear weather conditions. So that will be the first task of our curriculum. And then we will go into a more complex road geometry where we have rainy weather. And then we will go into an even more complex road geometry where we have got snowy conditions. And the idea is, if the agent masters these areas first, it will have an easier time in the more complex tasks. Another way to represent different scenarios is use this, what we call a scenario matrix. For example, on the x-axis, you can see that we have got different road geometries. We've got straight, U-turn, and the complete racetrack where you've got turns and twists. And on the y-axis, you've got different weather conditions, clear, rainy, and snowy. And the one way to combine these different tasks is just to consider trajectories in this matrix. For example, for the red scenario, we start with straight and clear, probably the easiest driving scenario. And then we keep everything in clear weather and we simply increase the complexity of the road. So that is one curriculum we can consider. Another curriculum we can consider is from straight and clear, we can jump into straight and snowy, and then we can go into snowy and complete. But the main idea is we are, of course, using heuristics so that we are always starting from easier tasks and we are going towards the more difficult tasks. But the way we go into the more difficult task is different across different curriculums. So keeping that in mind, we developed 5 different scenarios that consist of 3 different phases. For example, scenario 1 is we start at a straight road in clear weather conditions. Then we go into a U-turn, clear weather conditions, and then we go into a racetrack in clear conditions. So in scenario one, we do not actually test the weather adversely at all. We keep the weather condition constant, and we simply increase the geometry of the complexity of the geometry of the road. And for example, in the second scenario, we change both the road complexity and the weather conditions at the same time. So we designed all of this with different objectives in mind. Sometimes we keep some of the stuff constant, sometimes we change the weather conditions. And the idea here is to test, are we going to see different performance gaps between this, and which one is going to be most effective? And of course, in order to develop a baseline, first we take all of these tasks, road type and weather condition combinations, and we train a reinforcement learning algorithm from scratch. So the results that you, So the results that you see in here, these are the cumulative reward, the total performance metric that reinforcement learning algorithm gets for these particular scenarios when they are doing training from scratch. So there is no transfer or curriculum involved. We put a reinforcement learning algorithm here and we train it from scratch just for that condition. And the main idea is when we do curriculum learning, we should be able to do better than this metric. So these are kind of like our baseline performances. And what are these numbers? Well, this numbers is a reward metric that we have developed for this particular scenarios, and you can see the formula in here. And we basically, at every time step, we basically measure how much speed we are getting on the road. And we are also measuring how much we are deviating from the central axis of the road. So SP here is the speed of the vehicle. So we want to be as speedy as possible. And these are single car scenarios. So there are no collisions or other cars, etc. So we didn't consider that. But we also want to, stay on the central axis of the road. So this beta here is basically measuring our deviation from the central axis. And this TR post variable here is measuring our lateral deviation. So anyway, so when you combine this metric and measure it for the whole duration of the test track, so you get these numbers. So higher is better, basically. For example, if we look at the racetrack and snowy condition, which is arguably the most difficult objective to master, we got like the cumulative reward is in the order of 70,000. So whenever we do curriculum, we expect this number to go up. That is the main idea. All right, so we start with scenario one. And scenario one is we start from straight road, clear conditions. We go into U-turn, clear weather conditions, and racetrack and clear weather conditions. So after we complete one task, we transfer the knowledge to the second task. And after we complete the second task, we transfer the knowledge to the final task. And whenever we are doing all these transfers, we are actually keeping the total number of iterations constant, because at the end of the day, this is all about sample efficiency. For example, you can see that in total, we are going to spend 200,000 steps in the simulator. And we are going to keep this also, for example, for the 200,000 iterations, this is going to be the same number of iterations for baseline iterations. So we are basically comparing the performance gain that you get using same amount of samples for training from scratch versus using curriculum. For example, if you train from scratch, no transfer, no curriculum in the racetrack snowy, you got like 70,000 rewards. If you use the curriculum in here, you can see that you get almost 10 times more rewards, like 843,000 rewards. So this clearly shows the effectiveness of curriculum reinforcement learning. If you want to train on a complex road scenario, do not start from scratch. First train on straight, then go to U-turn. If you do these transfers by using total same amount of number of samples, you can get much better reward. So basically curriculum reinforcement learning, it is not only more sample efficient, it also gives you better performance. Okay, so what about other curriculums? Are they going to be as good as this one? So for example, here's another scenario. We start from U-turn this time. Instead of starting from the straight road in a rainy scenario, we go to a racetrack rainy scenario, and then we finally end up at a racetrack clear scenario. And the resulting performance that you get, this is still better than the baseline training. Remember, the baseline was about 70,000, so you got 144,000. But this is much less compared to the number that we get in here, 843,000. So you can clearly see that not all curriculums are equal. For example, if you want to get the best performance in circuit racetrack when in clear conditions, actually changing the weather condition does not help at all. You only need to focus on the road geometry. And although this agent was trained on harder scenarios first, that didn't really translate into the easier scenario. For example, here we go from more difficult to easier, and we don't see any performance gains. So other results are similar. Here's actually one of the worst ones. For example, what happens when we go from straight rainy, racetrack rainy, to racetrack snowy conditions. So racetrack snowy is the most difficult scenario. And you can see that in this case, we got 57,000, which is actually lower than the baseline performance that we get. So once again, we can see that just setting an arbitrary curriculum doesn't work. We need to be more conscious about this. And here is the best results that we get. So we got straight road, clear weather, racetrack, rainy weather, and then we go to racetrack, snowy weather. And we got over 1 million rewards, which is like 20 times higher than the baseline training. So basically, if you set up your curriculum in a mindful manner, like thinking about your objectives, and you can see that increasing the both road complexity and weather complexity at the same time incrementally gives the best results. So if your final task consists of a complex road geometry and complex weather conditions, then you need to increase both of them at the same time in your curriculum. So there are many more results like this, which I'm going to skip. I hope you get the the basic idea. And here are just a summary of all the results. The red lines are the baseline performances, and the curvy ones are our curriculum performances. And by the way, everything, of course, I showed you was mean performance. We do all of this training at least 30 times and average the results. And you can see that for most curriculums, you can go way above the baseline performance using same amount of samples. So one way to increase the sample efficiency of your simulation training is, if the task is difficult, never train from scratch, never directly attack the problem. Instead, design a curriculum for it. It will give you much better performance using lesser amount of samples. But at the same time, we cannot escape the heuristics in here. We need to be mindful about what kind of curriculum we are developing. But this can be seen as a hyperparameter, but I can argue that this is a much more insightful and easier to set hyperparameter compared to all the other deep learning hyperparameters we have, such as learning rates and coefficients. Setting up this kind of trainings and hyperparameters, they are much more intuitive. So whenever you want to reflect some domain knowledge into the problem, I believe using these meta hyperparameters are actually much more effective. Okay, so on to the second part. How am I doing on time? All right, I think I need to speed up a little bit. Okay, so the second part is about offline reinforcement learning. Okay, so one way to increase the sample efficiency of your simulator is, like, why are we doing things from scratch, right? I mean, why are we assuming that we don't know anything about driving and we want to let reinforcement learning agent to figure out everything? That is not the case in real life, right? If I want to develop an autonomous driving agent, I should already have some baseline performing agents. So how can I take the performance of these agents and put that as a prior to my reinforcement learning algorithm? Like, can I do that? And would that help me with my data inefficiency problem? So the classical way to handle this is called imitation learning. And what you do is basically you turn the problem into a supervised learning problem. For example, you've got an expert like you see in the video in here. Here you are watching an agent called IDM. It's a heuristic hand-coded agent, which just looks at the road conditions and by using some rule-based equations, it adjusts your speed and steering wheel. So that is how this algorithm works. And if you want to imitate this using a neural network, you simply collect the static data sets where the inputs to the data set are the measurements that you get on the road, and outputs are the labels are the actions of the IDM agent. And then this becomes a supervised learning problem. You fit a neural network to it. But the problem with this approach is whenever you do this and deploy that in real life conditions or even in simulators, you will see that this kind of approaches usually diverge very quickly, because it is very difficult to develop neural networks that generalize well outside of the expert training data. So if the data distribution is a little bit different than the expert, your errors are going to accumulate very fast and your imitation learning agent is going to diverge. So in that sense, it is also a little bit more difficult than supervised learning problem, because in supervised learning, your errors are static. You do an error and you forget about it. In this scenario, you do an error and then it accumulates and then you need to live with it. So one way to address that is called data aggregation techniques. So basically, whenever a neural network does a mistake, your teacher, your expert comes into the play again and provides you new labels where the expert, where your neural network is making mistakes. And then basically you collect more data, you enhance this, your data set, and eventually get good performance. There are a lot of successful demonstrations of this topic. But now, basically, you cannot work with static data sets. Like, you cannot simply get an expert demonstration and then learn from it. You still need to have the expert in the loop. So that is not very desirable. And experiments also show that even with having an expert, the performance is not guaranteed to generalize to unseen conditions. All right, so the premise of offline reinforcement learning is, what if I don't want to do imitation learning because of all these disadvantages? What if I take a static data set and do not use anything else, do not use any interactions at all? Can I just take that static data set and apply reinforcement learning to that and get a good performing agent? Hence the name offline reinforcement learning. So this is a very powerful premise because it basically gets rid of all your data inefficiency problems, because you don't need a simulator anymore. You don't need interactions. You just collect a huge amount of demonstrations, apply reinforcement learning to it, and hopefully get good results. So that is the main idea. I'm not going to go into technical details on how this can be done, but this is a very hot research area, and there are a lot of recent papers showing that this can be done in an efficient manner. And the main reason why this is different from imitation learning is, in imitation learning, you do not really differentiate between good behavior versus bad behavior. In imitation learning, you label everything as expert data, and you try to imitate that as close as possible. In offline reinforcement learning, because we are using optimization equations, Bellman equations, and value functions, etc., we can actually get rid of bad behavior and only focus on behaviors that gives us good returns. And then we can actually improve upon those good returns by using optimality equations. And this whole thing is, like I said, a very hot research topic, and there are a lot of there are a lot of nice trends in here. And this actually makes up a very nice framework where you collect demonstrations, you develop a reward function, and then by using offline reinforcement learning, you get better and better agents by evaluation and experimentation. And this actually removes the need for a simulator for the cases where your data is huge and it actually applies to the problem that you care about. And there are a lot of successful demonstrations of this in robotics. What about autonomous driving? Like, can we leverage this for autonomous driving? Again, this is very new. There are only a couple of papers that I know of that tries to apply this to autonomous driving. And here are our preliminary results. And here is our take on applying offline RL. So the first attempt that we are going to do is, we are simply going to use a heuristic policy, the IDM that I have shown at the beginning of this section. It's a nice policy. It's an handcrafted policy that works well for a variety of road conditions. And what we are going to do is, we are going to take the IDM and we are going to run it on the simulation and collect data. And of course, if you can afford to do real life tests, you can also do this in real life too. Here, data is cheap because we are not training anything. We are just evaluating stuff. And then we are going to take the demonstration data set of IDM, and then we are going to apply an offline reinforcement learning algorithm on it and see what happens. And when we try to do that, we actually see that results are not great. So this is the IDM policy, and the baseline evaluation is what kind of cumulative reward that you get if you run IDM. And the reward that we use in here is the same in the previous section. It basically measures how much speed you are making and how well you are aligned with the central axis of the road. So it's like a pretty good number. And then you take the static data set, you apply offline RL, and you get worse performance. So offline RL cannot successfully imitate IDM's success. And not only it cannot imitate the access, it also doesn't generalize well at all. So for this case, it is actually a disappointment. Offline RL didn't do what it needed to do. Okay, so what if I use a different agent? So instead of using IDM, now we go and train a reinforcement learning agent. Actually, we do not train it. We simply pick one of the reinforcement learning agents that we have trained from the previous experiments, and instead do a demonstration with that reinforcement learning agent, and then take the evaluation data set of that agent and apply offline RL to it, and let's see what are we going to get. In this case, we get much, much better performance. So the RL policy that we are using, so this is already trained. We are not using any extra training samples. We are not spending any extra samples on it. And the baseline evaluation is actually, it is, sorry, the numbers are a bit messed up in here. 302K in here. And when we go to the offline RL performance, we actually get a very, very similar performance in here. And this is good. This is actually great news. Why this is good news? Because the offline RL agent, it's actually achieved the same performance by just looking at the demonstrations of this agent. And training this agent from scratch, it actually requires more than 10 million steps. But then you take this agent, you only give a demonstration of 100,000 steps, and the offline RL can actually achieve the same performance. And this is achieved using only a static data set. This offline RL, it didn't collect any interaction data from the simulator or in real life. So this is actually very promising. And you can only get the same level of imitation learning performance if you are only using data aggregation methods like Dagger and all that other stuff, but that would cost you extra teacher time or expert time. Here, we are only using static data sets. And here you can see the performance of this agent. This is an agent that is trained on a static data set. It's a reinforcement learning agent, but it doesn't directly collect any data from simulator or in real life. And in favor of time, I'm going to pass this quick. I mean, it is actually easy to see that it gets good performance and it does its job. But then there's this question, why applying this on IDM didn't work and applying this on RL policy worked? Like, what is the difference? Because both of these, if you look at their evaluations, they are very close in performance. So they are both good policies. What actually changed when we apply an offline RL to it? So in order to analyze that, we looked at some data collected by the two algorithms. And one thing we have realized that if you look at the speed coverage of IDM, we can see that IDM is not really spreading this, its speed across the tracks. You can see that most of the speed that IDM is achieving is on a certain interval, and all the other intervals are less distributed. When we look at the speed covered by different speed intervals covered by the reinforcement learning algorithm, the second demonstrator, we see a much wider coverage. So it really boils down to data coverage. If you are getting demonstrations from an expert, we need to make sure that that expert is actually covering a good portion of our state space. Otherwise, our performance does not become generalizable. And all of this actually shows us that we really need a lot of good metrics on how to measure state coverage, how diverse our expert is, etc. So the main takeaway is if your demonstrator is covering a good portion of your state space, then you really you might not need to collect a lot of data from your simulator. You can do offline reinforcement learning. All right, the final part, I believe I'm a bit over time, so I will make this super quick. So the final part is on how to reverse sim to real and make it real to sim. So like I mentioned, most of the reinforcement learning that we do is what we call sim to real transfer. We train in simulation and deploy to real life. But of course, if simulation and real life are different from each other, this doesn't get you good performance. And to address that, we have been working on this architecture, which we call real to sim. And the main idea here is we first collect data from a lot of road tests, not necessarily autonomous tests. I mean, it can be any policy that we drive in here. And then we collect the traffic distribution and the traffic dynamics in here and extract a lot of statistics. And then we use that statistics to basically feed a low fidelity parametric simulator. So this is a generative simulator in the sense that you can put some traffic parameters into it and it will generate the traffic that behaves according to statistics that you feed into this simulator. And when we learn the traffic dynamics from real life, we inject that into a low fidelity simulator. And the reason why this is low fidelity is because it is very easy and very fast to train reinforcement learning agents here. So this is a very cheap simulator. And then after we train in the cheap simulator, then we go into a much higher fidelity simulator where the traffic conditions are more realistic, the driving models are more realistic, and then we validate this, our approach in the high fidelity simulator. And then once we are satisfied with that, we go into real life and deploy it, collect more data, and then do this loop over and over again. And the main idea is once you make this as a closed loop approach, then more data you collect from real life, your simulator gets better. As your simulator gets better, your real life performance also gets better. That's the main idea. And the particular results that I'm going to show today is going to be about lane changing decisions. So here, unlike the first two examples, we are actually just giving a high level decision by reinforcement learning agent. And the decision that reinforcement learning agent gives is whether should I stay in my current lane or should I switch to the left or the right lane to maximize my performance, but of course also while monitoring safety so that I'm not going to collide with other vehicles. So the phase one is, like I said, collect traffic statistics from real life. So you got this autonomous car, which is mainly just equipped with cameras and radars. We don't have lidars or stuff like that. It is only camera and radar measurements. And by using that, we can actually collect a lot of data on what are the relative positions between us and the lead vehicle, what are the velocity, and what are the follower vehicle position and follower vehicle velocity. So we can get all the statistics. And there are a lot of other statistics that we actually measure, but these are the main ones. And then we use that statistics to feed our generative models in the low fidelity simulator. And once we feed this into the low fidelity simulator, now we can do reinforcement learning in low fidelity. And in the low fidelity simulator, reinforcement learning agent simply learns, should I stay in my current lane? Should I switch to the left lane or right lane? For example, here you will see that once it is ahead of the following car, it will actually go into a left lane change. So we learn how to do that. And like I said, all the vehicle positions, speed, and everything, these are all based on the statistics that we collected. But of course, this is a low fidelity simulator. It doesn't really reflect the real life dynamics in the sense that vehicle dynamics. So we also have, we also transfer this policy into a high fidelity simulator, and we also conduct training and validation in here to make sure that our algorithms can actually cope with real life conditions. And finally, once we are satisfied with the high fidelity simulator, we go into real life. And we got great results actually. So after running this whole loop for a couple of iterations, this is some of the real life tests that we get from roads of Istanbul. For example, you can see that whenever there's an empty lane, our car successfully makes a lane change. And whenever there's a slow truck in front of it, it actually changes lane again. So we were able to conduct hours and hours of autonomous driving tests like this. And I believe the disengagement rates were very, very, very low. So most of the time, the driver is just monitoring and all the lane changes are executed autonomously. And in order to achieve this performance by just using simulator without not closing the loop, we were using billions of samples maybe. But after we started deploying this real life, real to sim, sim to real loop, we were able to cut down the magnitude of simulations that we are using by an order of magnitude. So the main takeaway is if you are doing simulation-based training, do not make it only one-way flow. Do not just do sim to real, but also consider real to sim, which will improve your overall simulation efficiency, and it will also give you a much more realistic agent. So these are the main takeaways away today. These are the main messages of today. RL is difficult to train. It is even more difficult to deploy, but as you see, the end result is worth it. But at the same time, in order to make this scalable, in order to make this more deployable, we need to come up with better approaches. We need to use curriculums, offline datasets, and real to sim. And I want to finish by thanking to all my collaborators, my students at the university, and also my collaborators at Eatron Technologies. And I also want to say a few words about Professor Pınar Boyraz Baykaş, who was a brilliant researcher that we lost last year. And I thought that this would be an appropriate moment to mention that, because 2 years ago in this very same workshop was the moment that we met for the first time. And I was really impressed by how professional she is, and also how of a nice and great person she is. She is greatly missed. We lost her at a very young age, and I just wanted to, remember her in this presentation. Thank you very much for your attention. And if you have any questions, I will be happy to take it. And here also are my emails in case you want to contact me later. Thanks a lot.
Thank you very much for the nice presentation and informative presentation, actually. Thanks a lot. We're a bit over time, but I think we can take some questions. We can make it up during lunchtime, I think. So are there any questions?
I would have a question.
Mm-hmm.
You're using Simstar, and it's also based on this Unreal Engine.
Yes. Yes.
And maybe you know this popular simulator called Carla that is also based on this Unreal Engine. So what is the advantage of Simstar over this Carla simulator?
Well, the main advantage is because we developed Simstar, we are much more comfortable with modifying it, so we can do all this crazy curriculum stuff, real to sim to real transfer. I would say also like generating randomized scenarios, plugging in other vehicle dynamics, etc. These things are much more flexible in Simstar. And like I said, because we have developed it, we are more comfortable with it. But you can also develop a lot of similar functionalities using Carla as well. And it's an open source tool. So it is actually, it might be better suited for pure academic research.
Okay. You generated scenarios manually, right? Is there a way to automatically generate these scenarios, maybe 1,000 of them?
Yes, yes. So I didn't put any results here because this is too preliminary, but yes, we are currently working on automated curriculum learning, where we are generating all these, curriculum tasks using statistical methods, which are all random. So that is something that you can do, and that is something we are working on right now, and hopefully we will be able to publish it soon. But yes, it can be done.
Okay, thanks.
Thank you.
We can. Okay.
I also have one question. Thanks for your
Sure.
nice presentation.
Right.
My question will be related to curriculum reinforcement learning.
Sure.
You mentioned about 4 scenarios, and in the last scenario, you included both road geometry and weather change as challenges.
Yes.
And you showed that you obtained the best result with this scenario.
Yes.
Even though you included both challenges, maybe I missed something in that part. Why do you think you obtain a better performance with scenario?
Well, there's no analytical explanation behind it, right? Like with most modern machine learning, there's no theory behind it. But my educated guess is, so if you go into this scenario, our target scenario is here is the most complex road geometry, and it is the most complex weather condition. So other scenarios basically show that if you just keep increasing only the road geometry or only the weather conditions, you don't get good performance. So basically you need to increase both of them at the same time incrementally. And the main reason I believe is, again, whenever you are transferring your agent between 2 tasks, they shouldn't be too similar or too dissimilar to each other. So in both directions. So I guess slowly perturbing both conditions at the same time kind of gives the best results in between. But if we want to get a good answer to that, we need to develop better metrics to measure similarity and dissimilarity between tasks. Does that answer your question?
Yes, thank you.
Okay, you're welcome.
We can take a final question from Domagoj Mastorovic, I think.
Yes, thank you. Okay, first of all, thank you for the presentation. I would have one question regarding the offline reinforcement learning and its relation to imitation learning.
Sure.
So you mentioned that the biggest advantage is that with offline reinforcement learning, we can actually kind of filter good demonstrations from bad,
Yes.
if I understood that correctly.
That's correct. Yeah.
And with imitation learning, the bottom line is that we basically learn all all demonstrations, because that's we have this assumption that expert demonstrations are the data that we want to learn. So my question would be more in regards to overall expert demonstrations. So how can we, so usually we would assume that expert demonstration, I mean, that all or maybe most of them are good because they're being done by the expert. So can you maybe a bit more elaborate? So when can or how can we kind of differentiate these, or how often does this happen? I mean, I had this assumption that basically if we have the expert demonstrator, then all the demonstration that the expert demonstrator does, we want all of them to be learned. And if that's not the case, then what are the, or maybe if you can just elaborate this a bit.
Sure. Let me try. So maybe the differentiation is more on not about good or bad expert. It is more about optimal and suboptimal expert. So even when we have an expert demonstration, it's good performance, but it's not necessarily optimal, right? And in the classical imitation learning, we do not really have a measure of performance. It is just, we've got states observed by the expert and then actions executed by the expert, but we do not have a reward or optimality function. We just want to fit a neural network in between. So what reinforcement learning does is, by using a reward function, it can actually measure how often, how close the expert is being into an optimal agent, how close or how far away the expert is away from being optimal. And the optimality here is measured using the Bellman equation. So if you satisfy the Bellman equation, you are optimal. So basically, by evaluating the fitness of the expert to Bellman equation, we can actually filter some of the suboptimal behavior that the expert demonstrates. And by solving the Bellman equation, which is basically what reinforcement learning does, we can replace those suboptimal with the optimal actions. So you actually improve upon the expert when you apply offline reinforcement learning. Of course, under some conditions, this is not possible all the time, but that is the main idea. When it works, it should actually give you a better answer than the expert. Does that make sense?
Yeah, thanks.
All right, you're welcome.
Okay, so thank you very much for your presentation. Actually, I had some questions, but maybe we can discuss it later, or I can visit you in Istanbul maybe. Yeah. Thank you.
Thank you. Thanks, everyone. Thanks.